To get things started, I'll just give a brief explanation of geothermal energy for those that might not be as familiar. Geothermal energy fundamentally represents heat that is stored within the planet's subsurface, going all the way down to the center of the Earth in the inner core, as you see here in the famous pi figure. This heat has been built up in the Earth's subsurface over billions of years from two primary sources. The largest one is actually the radioactive decay of certain radioactive elements in the Earth's crust, which can be quite prominent. And secondly is heat left over from the initial accretion or initial formation of Earth. And those two processes are responsible for building up enough energy stored in the Earth's crust as geothermal heat that provides more than enough to meet humanity's global energy needs in the foreseeable future. In fact, the total energy content stored in the Earth's subsurface from both planetary decay and the initial heat from planetary accretion exceed our global annual energy demand by a factor of 1 billion. And so tapping into a mere fraction of geothermal energy provides more than enough of our energy needs for the foreseeable future. And importantly, this is mostly carbon-free energy. It emits very low carbon emissions, and so is a suitable energy source for the future of our energy supply. In addition, geothermal energy is naturally complementary to more intermittent wind and solar resources, able to balance out the ebbs and flows of sunlight or wind blowing or not blowing. It also manages to balance some of the land and materials requirements, trying to build out an energy system fully dependent on those intermittent renewable resources. And so geothermal can be a great enabler for the energy transition of this next century. Now, in terms of how we tap into this geothermal heat today, there are a few varieties. Probably the most common and historic, of course, is simply bathing in naturally occurring hot springs that can be found throughout the globe, typically near volcanically active areas. But more recently, in the past 100 years, geothermal has been tapped for electric power generation. So this is whereby we go and find existing naturally occurring geothermal reservoirs today where hot water flows underground into rock through fractures, faults, through porous fractured rock, and comes back near the surface, near at the surface as hot water, if not steam. And so we have been able to tap into this expression of geothermal energy for over 100 years, dating back to the first plant in Lateran, Italy. Now, there's a few approaches here, as mentioned, in terms of how you can extract this higher grade geothermal heat. So far, the practice in the past 100 years is that figure all the way to the left, which is essentially tapping into naturally occurring geothermal reservoirs. There's posterity, I'll refer to as hydrothermal reservoirs for the rest of this discussion. You can also tap into these hydrothermal systems, not just for producing electric power, but also the direct use of heat for heating buildings, heating entire cities per se. And these hydrothermal systems are typically fed heat by either actual magma bodies underground or by occurring in a location where there is an unusually high geothermal gradient relative to the average gradient in the crust, which you can find in regions such as Nevada in the United States. Now, there are some more novel approaches for how we can extract geothermal heat from the subsurface without relying on naturally occurring hydrothermal reservoirs. In fact, this is really the big constraint on tapping into geothermal energy today, is that these naturally occurring reservoirs only occur in fairly niche locations, in particular locations that have a high geothermal gradient, which more often not means that they are nearby existing plate boundaries, volcanic areas. And so we don't see expansive geothermal development beyond areas like Iceland or the Western United States or areas along the Pacific Ring of Fire as it stands so far, because that is the main locations whereby you would find these naturally occurring hydrothermal reservoirs. but there are quite a few approaches where you do not rely on this Goldilocks combination of natural conditions to extract heat from the ground. In fact, there are means whereby you can extract that heat from much drier rock that's still hot. So temperature being the only requirement or parameter you're actually seeking to target in the Earth's subsurface. And those typically involve enhanced geothermal systems techniques. So this involves drilling a well, doing some form of stimulation that fractures the rock and creates flow paths, whereby you can flow cold water from one well to another, heating that water up along the fracture to produce hot water or steam at the surface. Traditionally, those systems have been targeting more crystalline basement rock that is atypical of hydrothermal systems, but there's also been more novel approaches looking now to extract geothermal heat from sedimentary-based reservoirs. Not shown on the figure, but another approach that's gained a lot of momentum in recent years are advanced geothermal systems, or often called closed-loop geothermal systems. This involves doing away with the fracture network and simply extracting your heat from the wellbore itself. So drilling a lateral or series of laterals between those two wells so that you are now harnessing heat solely within the wellbore and not actually interacting with the natural formation in terms of flowing that water through fractures. So that system has trade-offs in that you're reducing the contact area you would normally have with the fracture network in terms of extracting the most heat possible, but you have an approach that is proposed to be much more reliable in terms of mitigating against geological risk underground. Finally, the system that I want to talk about today that is the focus of our discussion, and especially what we want to target with our drilling technology, is this idea of super hot geothermal systems or super hot rock geothermal systems. What this basically entails is the EGS approaches on the left that I just mentioned, actually extrapolating those technologies and methodologies to depths and temperatures where water in situ is actually supercritical. So supercritical, or the critical point for water, occurs somewhere along a temperature of 374 degrees Celsius and about 22 megapascals, which comes out to around 300 to 350 PSI, which by drilling to those temperatures, you're almost guaranteed to be at those sorts of pressures. When water exceeds this critical point, what occurs is the difference or barrier, so to speak, between being in a liquid phase or a gas phase begins to shrink down to being almost negligible. And what you end up being able to achieve by getting a fluid up to supercritical, particular water, is you now are able to produce the higher enthalpy or energy density of a fluid heated to these temperatures while still retaining the densities similar to a liquid. It's sort of in between a gas and liquid in terms of density. And what this has implications for geothermal power production is to greatly increase, a step change increase in the power achieved or power produced per well. So this greatly improves the economics of producing geothermal from an EGS type approach, which often has challenges, even if mitigating the technical risk of producing economic geothermal power. The simplest way to improve those economics is simply increase the power produced per well field while not increasing as much the drilling costs or capital costs to build that well field. And we believe super hot, or targeting these super hot temperatures, is absolutely the approach that can greatly improve the economics of geothermal and actually make these geothermal systems economic virtually independent of location, because no matter how deep you drill, you are going to access very high grade heat that can lead to a geothermal well producing on the order of 20 to 50 megawatts of electric power. So that is a very significant 3 to 10 times improvement in terms of the power density per well in terms of producing electric power. Now, the challenge, of course, in terms of why we do not readily tap into super hot rock or super hot geothermal systems today is overcoming limitations to conventional drilling technology as it stands, getting to those temperatures, which essentially implies getting close to, if not exceeding 400 degrees Celsius in the subsurface, implies you have to drill quite deep, unless you are in unique locations like in Iceland or on the shelf of a volcano, whereby you could hit these temperatures at maybe 3 to 5 kilometers because you have a magma body not much deeper than that. If we want to actually expand the access to these super hot temperatures beyond those locations, we need a fairly disruptive drilling technology that is able to readily drill to 10 kilometers and deeper than that, on the scale of hundreds, if not thousands of wells per year. And this is simply financially prohibitive with existing technology, as was outlined in the United States GeoVision report that was published about 4 or 5 years ago on the future of geothermal energy. And so this GeoVision report actually kind of in one swoop eliminated supercritical resources from their analysis for this reason, that they couldn't surmise of drilling technology that can readily access these temperatures, which you can see here for the continental US. Even at 10 kilometers, you only see these temperatures in about 30% of the country. To actually really expand universal access in not just United States, but throughout the world, like Northern Ireland, for example, requires drilling technology that can access 10 to 20 kilometers replicably. And that's a significant technical challenge. There's very good reasons why we don't readily drill to those depths today. And it's not just because there isn't an economic reason to. In fact, in the late 20th century, the United States and Soviet Union had a quasi-space race that was a race to the center of the earth, if you could call it that, or rather a race to the mantle, which occurs below the crust at a depth ranging from anywhere from 5 to 100 kilometers. Both the United States and the Soviets set out on separate projects to drill this hole, and the Soviets were the party willing to withstand the exponentially increasing cost to continue drilling. This borehole became known the Kola borehole in the Kola Peninsula in northern Russia, and it took 20 years to drill just over 12 kilometers deep in terms of vertical depth. So it was a significant challenge and took far too long in terms of being able to drill these holes on a commercial scale for how long it took Soviet Union drilling this deep Kola borehole. And the reason for that is twofold. One, or can be summarized in, I think, two categories. One is that drilling, conventional drilling, gets slower as you continue to drill deeper and begin to access rock that is much different than the sedimentary overburden conventional drilling rigs would be operating in for, say, oil and gas drilling today. Once they are exceeding or drilling past this basement rock contact, which can occur anywhere from near the surface to 5 to 10 kilometers underground, you begin to now drill through rock that is almost uniformly crystalline in nature. It's quite hard and abrasive, and it's quite hot, of course. And so a mechanical drill bit begins to typically slow down as it enters these harder rock formations and cannot drill as fast as a softer sedimentary rock. The second reason, and actually maybe the more prominent for slowing down deep drilling, is actually the increased non-productive time. So there's a lot more time in these deep drilling operations that has to be spent not drilling, but doing things like tripping in and pulling out of the hole to replace drill bits, resolve a bottom hole assembly, remedy issues with stuck pipe or getting off center, or remedying issues with lost circulation. All of these issues begin to expound and build up as you begin to go deeper and hotter. And in the context of the Kola borehole, I believe the chief limitation of why they chose not to go deeper was they finally hit temperatures whereby their equipment began to fail repeatedly operating at those depths. So the temperature experience at these depths, actually independent of depth, can be quite a challenge to overcome with conventional drilling technologies that involve mechanical tools and electronics that have to be downhole and have to be cooled down below their rated temperature, which is often much lower than the in situ temperatures implied for targeting super hot geothermal. Now, that being said, the reality is this challenge is of drilling to 10 to 20 kilometers depth from a physical point of view is not anything particularly unique or extreme about it. It really is not drilling to the center of the earth and trying to see if Jules Verne's had a point in terms of finding a lost ocean underground. It's actually much more like barely pricking the skin of a grape. So we're only talking about drilling 10 to 20 kilometers in the crust. We're still mostly in the crust. We're not exceeding into the mantle unless we were drilling in the ocean per se, and nowhere close to drilling to the Earth's core. And so in terms of drilling into the subsurface, this challenge can seem relatively insignificant in terms of entire planet as a whole, but there's still the issue of how do we overcome the limitations to conventional drilling as I just outlined. The solution we have here that I would like to talk about is a technology that was conceived at the MIT Plasma Science Fusion Center about 13 years ago by scientists Paul Waskoff and Daniel Cohn, and that is millimeter wave drilling technology. And in essence, what this proposes is to replace all functions of a downhole drilling operation, so rock reduction, reducing rock to a size, particulate or particle that can then be removed from the borehole, so material removal, also being able to stabilize the borehole while you are destroying that rock and removing it out of the hole so you can continue drilling and managing things like temperature and pressure. What this proposes is to replace those functions that a conventional drilling rig or a drill string would provide with this energy matter interaction, dielectric heating. What dielectric heating is the same process responsible for heating up food in your microwave oven. And what it is delivering microwave energy, or really any RF energy, but particularly microwaves because of the benefits of their frequency, to a dielectric material or a material that absorbs microwave and other electromagnetic radiation. When a dielectric material absorbs that microwave energy, it is going to rapidly heat up because the molecules making up that material are dipolar. And so when they see a changing electromagnetic field, they begin to move around and buzz and heat up at the molecular scale. And with enough microwave energy, a dielectric material can not just melt, but it can actually vaporize. And that is exactly what we're proposing here. So there's a pipe that's in the hole. It's actually our only main equipment down hole in the borehole that is serving as a conduit for microwave generated at the surface with a device called a gyrotron, which I will get into on a later slide. This microwave is being generated and transmitted at a wavelength of around 1 to 10 millimeters, hence the name millimeter wave. And when that energy is delivered to the borehole bottom, the rock surface, being a dielectric material, will rapidly heat up and eventually vaporize. That rock vapor, of course, will very quickly condense because these are very high temperatures where rock vaporizes. It's around 3,000 degrees Celsius, give or take a few hundred degrees Celsius, especially for crystalline silicate-based rocks we expect to encounter. And once that rock particulate condenses, we are then able to convey the particulate up the borehole annulus with a circulating purge gas that is also injected down our waveguide or drill pipe, if you'd like to call it that. And so that purge flow is high enough to actually circulate and lift these particles up because they are so fine being produced from the vaporization process. So it's not an extreme flow rate. It's fairly practical by existing compressor and gas injection technology on the market today. Finally, while we are drilling this hole into the ground, we are not just vaporizing the rock, but we are also melting an outer ring around this vaporized hole that actually stays behind in the hole, and upon cooling, vitrifies to form a glass or glass ceramic lined borehole. And so this glass liner provides unique functionality in terms of not only stabilizing our hole while we are drilling, because given that this is replacing drilling muds with a drilling gas, this is a underbalanced drilling approach. This liner allows us to prevent any inflows of fluids coming into the hole while also retaining a structurally competent borehole during the drilling process. The net implications here are that we can have a drilling process that operates fairly independent of depth. The dielectric heating does not depend on pressure, and in fact, it becomes more efficient as rock gets hotter. And importantly, there are no reasons for those temperatures and pressures to cause our drill string here to fail. So it should reduce non-productive time and result in a drilling process that performs fairly linear with depth. In other words, the drilling cost, which is important, will not increase exponentially with depth. Now, the reason we're able to take this approach is twofold. And one is that the wavelength we're operating at, millimeter wave, which is a frequency of around 30 to 300 gigahertz. This is a sort of Goldilocks region, particularly for drilling geothermal sized boreholes, because not only do we have a wavelength that has efficient absorption into the rock, most of the microwave power goes into the rock for heating and vaporizing. But we also have a wavelength that can be transmitted over very long distances very efficiently, which you see here in this figure on the right. We can achieve transmission distances exceeding 90%, so less than 10% loss along very deep boreholes that could be 10 to 20 kilometers long, so that we guarantee the vast majority of that microwave power ends up at the bottom heating rock versus being lost into the waveguide or other areas of the borehole environment. Secondly is the device that is our source for the microwave energy, and this is a gyrotron. Gyrotron technology and a lot of these high power millimeter wave equipment were primarily developed, designed, and built dating back to the 1950s, related to research in nuclear fusion. So the primary function for these gyrotrons today is being used in nuclear fusion experiments where they want to use microwaves to heat plasmas up to millions of degrees Celsius for a fusion reaction to take place. In contrast, we're wanting to heat rock up with these devices at 3,000 degrees Celsius, which makes it sound a bit more modest than attempting nuclear fusion, although certainly exciting for the potential there. Gyrotrons sit again in a sort of Goldilocks region where they generate the wavelength we want for long distance transmission, which is millimeter wave, but they also provide the power output that we require for drilling a full-size geothermal borehole at the rates of penetration that we want to be economic. Finally, I'll touch briefly that in terms of assembly following the gyrotron, there's primarily the downhole waveguide, which, as you see in the figure on the right, is primarily a pipe within the hole that's the conduit for our microwaves. But there are a variety of transmission line components at the surface that do the job of redirecting that microwave beam to go down the borehole, managing issues like, say, reflected power or microwaves that could be reflected back to the gyrotron, ensuring those are isolated and prevented from reaching the gyrotron itself. And of course, what's not shown here, all of the surface infrastructure for injecting gas at the wellhead. Finally, I'll touch briefly that these are images of the glass liner I was talking about earlier that is actually formed along the borehole wall after the vaporization process. In terms of the drilling operation, I believe I've already covered this, but to reiterate this, we are proposing a hybrid drilling operation that doesn't just drill with millimeter wave drilling, because we know that is not the most optimized process at the surface. One, those are the types of geologies or subsurface risk that would give challenges for millimeter wave drilling, primarily non-silicate rocks, overpressured aquifers, and also encountering oil and gas. These are going to be technical risks we primarily encounter in the sedimentary overburden before we get down to the basement rock. And so we propose not to replace conventional drilling at what it does best and actually start at the surface with conventional rotary or drag-based mechanical drilling tools. And it's only when we penetrate the basement and get to a depth where we see diminishing returns on that conventional drilling operation that we actually switch over to the millimeter wave drilling assembly and continue until our ultimate depth target. And so ultimately, this system will look like a very conventional onshore drilling rig that simply has these millimeter wave technology components integrated within that architecture. In terms of drilling costs, as I mentioned, we believe that the technical advantages provided by this approach enables a linear cost curve for drilling. In other words, compared to conventional drilling, which gets exponentially more expensive as you go deeper, the millimeter wave drilling process operates fairly independent of depth. And our projections show that with the capital cost of these equipment considered, and presuming we can achieve our rate of penetration target of 1 millimeter per second or 3.5 meters per hour, we can actually drill these deep geothermal holes at a rate of $1,000 per meter. And this is very important for the overall cost model for a super hot geothermal plant, that delivering these wells at a similar cost to what geothermal wells are drilled today, albeit a little more expensive, enables levelized cost of electricity that can beat $40 per megawatt hour. So these deep super hot systems can be economically competitive with wind and solar resources today without even taking into account their advantages in terms of being a baseload resource that is always on and has a high capacity factor and the ability to fluctuate that power output depending on what the market requires. Finally, I'll give a few minutes to talk about Quaise and our current status. We've raised over $70 million in private capital, and that fundraising also includes a $5 million award from the ARPA-E agency within the Department of Energy that particularly funds high risk, high reward, early stage technology projects like ours. In terms of our team, myself and Carlos Araque are the co-founders, and Carlos is our CEO. We have an engineering team based in Houston, led by Henry Fountain, a research team based in Cambridge, UK, led by Frank Monmouth, and a business development team in Boston, led by Kevin Bonebrake. So we have an engineering, research, and business team all moving towards the same objective. And finally, all the teams, along with a few other parties external to Quaise, are involved in the ARPA-E testing campaign based in Oak Ridge National Lab, which I personally oversee. That Oak Ridge testing is taking place right now and is utilizing a much older high-powered gyrotron at Oak Ridge to provide a source of microwave power to advanced drilling experiments initially performed at MIT. MIT is where the technology got started, and Paul Waskoff was able to achieve small 2-inch deep holes, but was very limited by the power output of his gyrotron. He needed a much more powerful gyrotron, in other words, to actually make further progress. And so that is what we were doing here at Oak Ridge, utilizing their 200 kilowatt gyrotron and this large waveguide transmission line you see here for drilling these much larger rock targets with an end goal of drilling a 10-to-1 borehole by, it did hit that this past year in 2022, but this year to drill a 10-to-1, then a 100-to-1 borehole that's now getting first 3 feet and eventually 25 to 30 feet deep into a rock target. And so that's utilizing this apparatus shown here to provide the rock target and lifting that rock up and down relative to the fixed waveguide. We also have a smaller system at our Houston engineering facility that is similarly purposed to demonstrating drilling through small rock samples that are much larger than what was achieved at MIT. This is working with two klystron systems, which are fairly close cousins of the gyrotron and provide a power output here of around 15 to 30 kilowatts combined. And so we've used that system to drill a small 10-to-1 hole and are continuing to do testing with that system in parallel to the Oak Ridge experiments you saw in the previous slide. Finally, there's also the engineering effort for developing the first prototype millimeter wave drilling rigs that can mobilize out into the field for our first field demonstrations, which incorporate all the core things shown here. Primarily is integrating a gyrotron and the high voltage supporting components within a more conventional mobile or fixed drilling rig architecture. Some of these systems are much more standard, in particular wellhead design and having a mobile or fixed transportable drilling rig like shown here, which will need to be the full scale for a geothermal sized drilling rig. This effort's actually in collaboration with Neighbors Industries, who's the largest manufacturer of onshore drilling rigs today. And Neighbors is helping us integrate our millimeter wave technologies within one of their existing rig architectures for the first prototype geothermal scale, full scale millimeter wave drilling rig. And so this system is expected to come online in the next 2 years. In the meantime, we have a much smaller system that is truck mounted that is intended to perform the first field demonstrations within the next year. So right now we are still in the lab proving out the technology to hit those deeper milestones like the 10 to 1 and 100 to 1 I mentioned previously. But we have this parallel effort within the engineering team to develop mobilized systems that can mobilize and do the first field demonstrations in the next 2 years, so that our goal is by 2026, we were able to drill our first super hot geothermal well, albeit at a shallow depth, and begin to actually develop geothermal projects while we continue to mature the drilling technology to deeper and deeper depths. With that, I think I've covered what I wanted to say in our slides here, and I'd like to open it up to questions and hope I didn't take up too much of the full hour.